I'm going to present a real-time private membership test using homomorphic encryption. This work I did in partnership with Homer Gamil and Mihail Maniatakos from New York University, Abu Dhabi. So first of all, what is private memberships test? It is the ability to privately check if an element is part of a set or database. So as you can see in this schematic, a client wants to check if an item, this document, is part of a database of a server. But the client wants to do that without telling what the item is to the server. So this is the private membership test. So where the private membership test is used. One example is a URL deny list application, which is used to prevent phishing attacks. In this type of application, links in our emails are replaced to links to a third party. So once we click this link, we're actually going to this third party, and they will going to verify if the link we are trying to access is malicious or not. The third party does that by checking if the link we are trying to access is part of a malicious database that they have. If it is part, it means it's a malicious website, so they block the access and alert the user. Otherwise, they just redirect to the site. However, there is a huge privacy concern that comes from it, which is that now the third party has the ability to see what every user is opening. So how can we mitigate this problem? We want to make the query private, so the server will not learn what the client is trying to open. However, the server could just send this database to the client, and the client could check locally. But the server is not willing to share its database, so the database has also to stay private. Another thing is that we have to operate in real time, because no user is willing to wait minutes or even seconds to open a link. And finally, we need the ability to update this database, because new malicious websites may be added or maybe something needs to be removed from the database. To solve this problem, we propose a solution using Bloom filters, which is a probabilistic data structure, and homomorphic encryption, which is a type of encryption that lets you operate directly on encrypted data. Our first step is to represent the database as a Bloom filter. To do that, the server has a database with a set of entries, and then the server passes each of these entries to a set of hash functions, and we get a list of integers as a result. And then we have an array of integers, which we increment at those integers that we got from the hash functions. And this results in a Bloom filter that represents this database. Now, how can we check if an element is part of the Bloom filter? To do that, we have two examples here. One that is part of the database, XXX, and ABC, which is not part of the database. So what we do, we pass through the same set of hash functions, we get a list of integers, and then we query this Bloom filter at those indices. And if they are all evaluate to true, then it means it is probably in the database. And if any of them evaluates to false, it means it's not in the database. I said probably because there is a chance of false positive will depend on the parameters of the Bloom filter. And now, how can we insert or delete an entry in the database? To do that, we have an example here, ABC, and the server wants to add this to the database. So the server is going to hash this through a set of hash functions. We'll get a list of integers, and then to insert is just going to increment the Bloom filter at those indices. And to delete, it's similar, just the difference is that the server will decrement at those indices. So how do we protect the client's query? Originally, we have the Bloom filter with indices going from 0 to the size of the Bloom filter, and the value set according to the database and the hash functions. Then what we do using homomorphic encryption is to shuffle this Bloom filter in an order that is only known to the client using the client's evaluation key. This effectively will create another layer of indexation, which we call position. So these positions are in plain text, and they go from 0 to the size of the Bloom filter. And then now we have the indices in this encrypted form in an order that is only known to the client. And the values are according to these indices and not according to these positions. So when a client wants to query, what the client does is simply to do again the hash functions and get the integers. Then the client is going to convert from these indices to positions. And these positions are what the client requests to the server in plain text. Now the server simply return this encrypted Bloom filter at those positions. So for example here, the client asks for the position 10, and the position 10 is this position here. And so the server is just going to return this position here in the encrypted Bloom filter. And the server doesn't know that this position 10 is the index 9. Okay. Now the client simply decrypts the result, and by knowing that the position 10 is the index 9, position 16 is the index 15, and so on, the client can figure out if the query is part of the Bloom filter or not. And this whole process has complexity O1. Now, how do we insert or delete an entry in this encrypted Bloom filter? So to demonstrate how this is done, we have here an example where the server wants to insert this entry ABC into the Bloom filter. For that, the server will hash it through the set of hash functions and get a list of integers. And these integers represent the indices that we have to increment. However, the server doesn't know where these indices are. So what the server has to do is a linear search. It is going to go through all the elements of the Bloom filter and check if the result of this hash function is equal to this encrypted index at that position. If it's true, it's going to increment the encrypted Bloom filter. This is just an example of the algorithm. The algorithm has to be data oblivious, and we have all the algorithms in the paper. Since this algorithm is a linear search, it has complexity O(n). We implement our solution using the BFE encryption scheme, which is a homomorphic encryption scheme, so we can operate directly on encrypted data. It supports batching, so we can pack many plain text into a ciphertext and operating on this plain text in a single instruction, multiple data fashion. So with that, it means we can pack many indices and values inside the ciphertext. And then each slot of the ciphertext can hold one of these indices and values. However, since the client is going to be accessing a ciphertext, there is no point shuffling the indices inside the ciphertext. So to improve performance during setup, one thing we can do is to keep the indices inside the ciphertext in order and only shuffle the indices of the ciphertext. So it's only shuffle the ciphertexts. So instead of having to shuffle n elements where the n is the size of the Bloom filter, we have only to shuffle the size of the Bloom filter divided by how many elements we can fit in a ciphertext. So now I'm going to show the results, which you ran in a single thread of an i7, but these algorithms are highly parallelizable, so we can improve performance significantly by using many threads which are available on servers. These results are for the element-wise representation, which we call ES, and for the group-wise representation that we call GS. And these are the parameters we use. A false positive rate of is inferior to 10 to the minus 3. We use 6 hash functions, and these are the parameters for the BFE encryption scheme. As you can see, the query time for both implementations is constant around 0.3 seconds. And the slowest process here is the setup, which is complexity O(n) squared. For the ES, it quickly grows and becomes prohibitive for database in the thousands, but for the GS, it's still practical for database in a few millions. And remember, since we can use more threads, we can expand this feasibility a little further. So now to summarize my presentation, we evaluate the design in the context of IRL dynamics application. We propose a solution that can query privately with complex O(n) under 0.3 seconds. It enables insertions and deletions. And also we optimized it for the BFE encryption scheme, which made the setup protocol practical for database of up to a few million entries. So I would like to thank you for watching, and if you are interested, our code is available on GitHub. Thank you.